This video is to showcase the road so far when it comes to the age-old question between flat earthers and heliocentric enthusiasts. Which comes first, the chicken or the high-pressure system existing next to the low-pressure system without a container? This has been a major point of contention in flat earth for many years, and we haven't really got any satisfactory answers out of it. In this video, I'll showcase two possible answers that were recently given, and one answer was a little older. The first video is from the first video clip after the explanation of the thought experiment will be Jaron and Witsit gets it asking Bryant Myers to explain the thought experiment, and the second clip will be from Kyrie, aka Flat Earth Boxer, aka Powerful Black Man with a Library Card, aka Young Moses. The purpose of this video is not to demean anyone or attack anyone or put them down. This is just to create a record of the types of answers that we've received, and if anyone has a better answer, you're welcome to respond to the video with your own video. And actually, that's actually what I'm encouraging to happen, so we could have a big compilation of records to set it straight, to keep the argument preserved so people can follow it as it's progressed. All right, without further ado, I'll let Jaron take it away with the explanation.
Or not. So this is the test that we are, asked the physicist. He had no answer, and I have not seen anybody who has any answer yet. But let's just say that this is a vacuum chamber. Okay, so we're not even saying we don't have to do the whole has to have a container. We'll use their container. Okay, so let's say that we evacuate the air and create a vacuum, but in this box, okay, we keep air. Okay, so let's say it's sealed, and we're going to draw some air in here. Okay, so the box is full of air. It is sealed. We got a sealed top. We evacuate the chamber, leave it to be a vacuum, and close the top. Okay, now we've got a vacuum. We've got a box with air in it. If we electronically somehow pull that little slide door back, okay, electronically this door opens. What's going to happen? What's going to happen? Is the gas going to fill the available space? Or is the gas going to sit on the ground because of the gravitational pull downwards? Okay, the answer is simple. And the answer destroys their entire model. Entire model. You cannot in any way think that this is going to hold the gravity in the box or hold the air in the box. The air goes to space. Now, they can say whatever they want. Well, there's a gradient on Earth. And okay, yeah, so the gradient on Earth is there's a lot of air here, and then it thins as it goes up until you guys say it gets to the vacuum. Great. But what is holding this? Because if you're telling me it's gravity, then gravity would hold this. So it makes no sense. Doesn't matter if you have a gradient, doesn't matter if there's no gradient, doesn't matter anything. All that matters is gravity is not strong enough to hold air to the ground when it's got an option of going to a vacuum. And that's just the way it is. So again, they don't have any answer for this. There's not been one person that has been able to say anything. They can't say anything. Okay. Anybody who believes that this would magically stay to the earth is darted. Probably severely mentally darted. Okay. We want to be careful of those people because they are running amok and they think that they're smart. That's the worst part about it. And I'm not even claiming I'm smart. I'm just saying I can look at things and be like, let me see how this works. Let me weigh this against evidence. Let me see what I feel. But I'm always open to changing my opinion. So if somebody wants to come forward and tell me how this will work in practice, then I'll listen. And I will stand up and say, I was proven wrong. If they give me some sort of answer that works. Because to me, there's just nothing. First, I was told when I used to tell the story, I used to kind of draw like, I think I did a video. Whoops, don't do that. What did I just do? Okay. First, I did a video where I was talking about if we had, and it's kind of the same story. I'll use this back button. There we go. So I told the story where if we basically had a chamber And I thought that this was good. If we had like a wall here, okay, so let's say there's a wall that's kind of like this. And okay, so there's like a shelf here that blocks these two sides. And it does have a little trap door that opens a little, a little sliver of this or something. Okay, so then it will open if we ever need it to open electronically or whatever. Okay, so that's a little window. So if this was all filled with air, and this was vacuum, and again, we open the slot, the air is going to leave into the vacuum. So that's just the way it is. Now, according to them, they would say, well, no, there's a gradient in here. It gets thinner as you go up. And just because this is adjacent to a vacuum doesn't mean, it just means that the vacuum is going to take some of this. It's just going to take some. Then you say, okay, I get it. What is holding the rest of this down? Why wouldn't it also exit? Their answer is gravity. So if that's the answer, then in this test, why wouldn't gravity hold this tiny little bit of air? It's a tiny little box. You're telling me it holds the entire atmosphere of the Earth. And you can't say, well, it's a different Earth. No. In my example here, we have the same ball Earth under it. It's on Earth. So if it can hold all the fucking atmosphere, somehow magically here, then it must hold this little bit. Hold on. Let's say that there's a box that is sealed. It's got air in it. Okay. We suck the rest of the air out of the room so that there's just the box there with the air in it. When we slide the top off the box, will the air then stay at the bottom of the box because of gravity?
I don't know what you're trying to say. Gravity.
Why don't you just listen for a second? Listen. If you're in a room,
I am listening.
Okay, then answer the question. If you're in a room and and we suck all the air out, but there's only a box in the middle of the room that has air in it, and then we remove the top of that box, where's that air going to be? Is it going to stick to the Earth, or is it going to?
How does that relate to the?
I'm asking you a question. Doesn't matter how it relates. I'm just asking you. I want to know
because you said that the gravity holds the air onto the Earth, and the air gets thinner and thinner and thinner. Okay, so we removed all of the air out of the room, so there's no pressure from the atmosphere pushing down on this box. We open up the box. Gravity holds the air in there or not?
Yeah, but do we still have gravity or not? Are we
yes.
trying to say
yeah, we have gravity
on your Earth. Your gravity, yes, on your Earth.
But have you actually done that experiment to get down to a zero vacuum?
Yeah, people have done that. People have put a chamber inside of a vacuum chamber. It's not that hard to do it.
Okay,
yes. But here's the thing, Brian. If the answer is the air would not come out of the box, then the entire pressure gradient next to a void is off the table. No. And here's the other thing: there's nowhere in science, nature, or anywhere that you can have high pressure next to low pressure without a container. Nowhere, anywhere.
What do you mean
ever?
High pressure next to low pressure?
Any higher pressure next to lower pressure or no pressure in any orientation. It doesn't matter.
Listen, do you have a little app that can measure the pressure in your house, the atmospheric pressure?
I don't.
You can
why would you not answer his question?
No, listen, I'm answering his question. You can literally measure the pressure at one altitude and go up and higher and see that it drops at altitude.
Okay, but he asked you what would happen to the pressure in the box.
Next to higher pressure. That is lower pressure next to higher pressure. You can measure that provably.
What would happen with the pressure in the box?
The kinetic theory of gases says that gases are going out fast. So, but when you have the sheer scale of the Earth and the gravity well of planet Earth, they're not going to go outside of the gravity well. They might in that room scatter around because gases do that. That's the kinetic theory of gases.
But what's different about it? It's the same gravity
on the surface
of
the
Earth. Same gravity is pulling.
Yeah.
I know, but you're not looking at the whole. Those gas molecules aren't going to escape out into space. Gravity is actually pulling on them, but you have to look at you have to do the calculations. You got to say, okay, here's what the kinetic theory of gases says, and gravity is going to pull down. There's going to be some energy that may be moving them around, but gravity is still there pulling them down. But
isn't gravity stronger at the surface though?
But there's other forces than just gravity. You guys realize that, right?
I'm just asking like a simple question. Isn't gravity strongest at the surface, or technically at the center of mass, right? So the surface.
But it's a very slow. It goes off very slowly, though. You see, so that small gradient. It's not a very fair experiment because you've got to get on a larger scale to see a big difference in the gravitational field.
Do you not see his point though? Like if we take gas and it's in a vacuum on the surface where the gravity is the strongest. It goes in all directions.
I know, but
so how would it stop it next to a vacuum where gravity's weaker?
the gravitational field of the reason that's because you see less gas up there, right? So that's the reason why there's more pressure at sea level, because it does have less.
That's
and
a
less
non
gravity.
sequitur to the question, though.
It isn't. This is why you're getting close to a vacuum at 100 kilometers up. It's almost a vacuum.
Yeah, you're just
I mean, so
you're
if the
repeating the same
carbon
thing.
So this gradient is because of gravity. That's why, the gravitational field decreases with altitude. That's why, less and less, you get.
That's a begging the question fallacy.
Well, what are you trying to? I don't understand what you're trying to.
We're saying it. Listen. If we have gas pressure in a container on the surface and it's next to a vacuum, once we open that box, it's going to fill the vacuum violently, right? It's immediately going to seek equilibrium. Second law of thermodynamics. Second law of thermodynamics. The gas is going to fill the vacuum because high pressure goes to low pressure, right?
Kind of like this railroad tank truck, how it just implodes like this.
It has nothing to do with what we're talking about, but
yeah, why can't you just hear me out and answer?
Just listen to Austin.
I'm just trying to understand what you're saying.
So listen to Austin. Just listen to him. He's going to explain something. Just listen and take it in.
Yeah. So like if we have a container of gas on the surface of the earth, and then we have a vacuum chamber and we open the gas next to a vacuum chamber, that gas from the container, once we open the lid, it's going to fill the vacuum violently, right? It's going to immediately seek equilibrium and fill that vacuum, fill the available space. And that's on the surface where gravity is the strongest.
I know, but the gravitational field is still acting on all those particles, but there's other things going on. Again, the gases they have a lot of motion and energy. So
that's what we're saying.
Yeah.
Actually,
I know the reason, because at the surface of the Earth, the temperature actually makes gases move faster. So that's the problem. When you have something like a gas, you've got a higher temperature. That's where they're going to move around. So gravity's still pulling on them, but there's other factors at play there besides just gravity.
Vacuum chambers are actually not very warm, bro. So even on the surface level, when we have a vacuum chamber where it's not warm, the gas is still going to immediately fill the vacuum. The point is that it's filling the vacuum, and if it's at the
isolated experiment, if you want to send me the experiment, fine.
You can do it a million times, man. Do you not see the intrinsic contradictory nature of what you're saying?
Did you see the contradictoriness of what you're saying?
You're using one little isolated thing.
It's not an isolated thing. We're trying to explain to you that gravity isn't sufficient to hold down gas when it's adjacent to a vacuum.
Gases have kinetic energy and they're moving around.
That's what we're saying.
I know, right? But I'm saying when you've got a large scale of a huge 6 sextillion ton Earth, that creates this gradient of different pressures. So yes, you've got a lot of movement going on at every. Nobody doubts we have storm systems. I mean, we've got all kinds of stuff going on. But as a whole, the gravity is keeping everything.
But it's not. It doesn't keep it down on the surface where it's the strongest. And the strongest vacuum we can replicate is like 10 to the negative 6 torr, right? They claim space is 10 to the negative 17 torr. So that's where gravity is the weakest. It's next to a much different pressure differential.
But vacuums aren't sucking things out. I mean,
no one said that. Gas fills the space. Vacuums don't suck. That's another non sequitur.
The gravitational field is what's keeping everything in place. That's why.
So why doesn't it keep that air in that box in place?
Okay, so well, again, I haven't done that experiment.
Okay, but you don't even need to do the experiment. Just think about it and let's pretend.
Yeah, use your mind and
let's pretend.
I'm using my mind, but you're using a little tiny room.
Okay, no, hold on.
Instead of like entire huge, a huge. I mean.
So you're saying that the little tiny room gas or the little tiny room vacuum is stronger than the vacuum of space?
I'm saying that gravity is pulling down on those gas molecules, but they also have a kinetic energy, and there's a lot going on there that you're just.
So why doesn't the kinetic energy of our atmosphere go off into fill the void of space?
It actually does. We lose atmosphere every.
And who told you that? And where? How did you measure this?
This
is just a theory. This is just a theory.
I've actually heard Dave Murphy saying this. Is it some kind of like you're losing atmosphere? I'm like, yeah, you're right, Dave. We are. But we got about 150 million years based on this calculation of atmosphere still left.
A theory.
So we can one of your own flat Earth people has brought this up at a debate.
Okay. Well, you're appealing to they're talking about how your model has a theory.
I'm saying that we do lose atmosphere every day, and it's actually a lot, but it's compared to how much atmosphere there is, it's a small amount.
That's what we're saying. That doesn't make sense. That's not how the second law works.
I know, but it's
why does some escape and not all?
It's because again, it's a little. Gravity's holding it. It's a statistical thing. You got a little bit of gas at the fringes,
Statistical. Is it like rolling? Got gravity's out here shooting dice, bro?
No,
Like,
it's, you just have, because there's a lot less up there, there's not that much that's going to come out. But yeah, because the pressures are so low, there is going to be some of this that will, escape out. But
but then
just
the stuff
debunks them.
lower, the stuff
It's such a
lower down is
small-
being held by
it's
the
such a
gravity,
small
right?
percentage, yeah, to what's left. So,
Okay. Yeah.
Just debunks the model, bro.
it doesn't debunk the model.
It does. It's physically impossible. It's contradictory to natural law.
Calculator is that it turns out for black holes, CE black hole is equal to CV black hole is equal to 0. From the perspective of particle physics, this is an incredible fine-tuning, because particle physics tells you that, which in turn is just proportional to the imaginary part of the Feynman propagator of the time-warp product of two Q's by the optical. The matching calculation is telling you that B minus of omega is proportional to the.
That much the previous question is that, like the previous one, the one that you have right in the front, you relate to.
This one here.
Right.
So classical observables depend only on G retarded, and G retarded of omega looks like an integral of A plus over omega prime minus A minus. This is any row. So if you could write down the density matrix for the coherent state, the same thing would happen.
One more question. So this question is a favorite preface. The last week, an interview between a science journalist and Dr. Svetlana Verdunjiga, and a world leader in exoplanetary and astrobiological research, surfaced in which the journalist presents a series of questions about classical physics and planetary science, which she, despite her unrivaled expertise in the field, did not answer, even to her own satisfaction. The interview ended with her becoming a little discourteous and in a state of denial. So the question is, given the popular heliocentric model, what experiments do you know of that evidence that the Earth is currently moving at an average speed of 66,000 miles per hour, or Mach 88 in an elliptical orbit around the sun, or spinning at an almost twice the speed of sound, or moving in any way at all consistent with the proclamations of the widely accepted heliocentric model?
I'm not an astronomer.
Would that be a no? You don't know any?
Me personally?
Yes.
I'm not an astronomer.
Is that a no? Okay. So the last one, the third one, I guess, in the interest of everyone's time.
Okay.
Can you think of any experimental demonstrations of gas pressure without a container, or adjacent to a vacuum without a solid barrier?
Okay. So I'm not a statistical.
Are you a physicist?
Marginally.
Okay.
I'm on board.
Can you think of any experiments today that you can do today that can distinguish gravity as a force as distinct from the effects of density and buoyancy and fluid medium?
So I'm not a fluid mechanics
Physicist, though.
Maybe, I don't know. You have to ask my advisor.
This is the hard one.
I know you can ask the crowd.
A physicist doesn't have to know
It
everything.
doesn't have to. I just wanted to see if you knew anything.
Because it's very specialized question that you're asking. You should go to, very specific.
She retarded.
You start Dr. Bogosian.
Hi.
Kyrie, nice to meet you.
Hi, nice to meet you.
So, Mr. Vataspati, or Dr.
Yes.
Vataspati, he's recommended. So I've come to 2 or 3 of these cosmology colloquiums,
Yeah.
and he's I've asked these 2 questions, and he's recommended that I ask the cosmologist these questions because
Okay.
the physicist prior could not answer them.
Okay.
The first question is, and this is perfect because you do tests of gravity.
Yeah.
What experiment have you come up with that, or have you discovered or seen that evidences the existence of a force called gravity, which as distinct from the effects of density and buoyancy in a medium?
What evidence there is for gravity?
In the experimental. As distinct from the effects of density and buoyancy in a medium.
The fact that planets move around, lots of evidence.
So I meant experimental evidence. So
That's experiment.
what's the independent variable in that experiment?
Okay, I guess you could look at different
Or control.
samples. I mean, you can drop things in a vacuum.
So things are more dense than 0. I mean, so a vacuum there's a 0 medium, so everything's
You can
equally
drop
more dense.
Objects.
As
You
distinct-
just take a room,
Yeah.
evacuate the air, and drop
Right.
things, and then they all fall the same.
Equally more dense than nothing, right? They're both equally. So it's distinct from the effects of density and buoyancy.
Yeah.
So gravity is a force that's
Yes.
it has nothing to do with density and buoyancy, right?
Yes.
It exists there whether or not.
Yes,
Right.
it's
So when
the-
things fall in a medium,
Yes.
it's because they're equally more dense than nothing. In a vacuum, they're equally more dense than nothing. That's why they fall at the same rate. So the question is more as distinct from the effects of density and buoyancy.
Yeah.
If no, that's fine too.
I'm not sure I can add more than I said.
Then the second question
Yeah.
is, so your cosmology depends upon. So the second law of thermodynamics stipulates that you can't have a gas pressure system in the midst of a vacuum. Like a high pressure always goes to low pressure.
Yes, that's true.
So has it been brought up within the field of cosmology that the heliocentric cosmology depends upon a violation of the second law of thermodynamics?
What
in
is
order
a heliocentric? Is it
The heliocentric model being
centered around the Earth?
heliocentric means, or let's say the cosmological model assumed within the parameters of the general relativity theory, whatever you decide is the center of the universe. But normally you have gas composed stars in the middle of a vacuum. So
So yes, you're right. So if you have gas, it would
Right.
expand into the vacuum. Absolutely.
So do you know of any demonstrations of gas pressure in the middle of a vacuum without a solid barrier between the two?
No.
So would it be true to say that the cosmological model that underpins the assumptions of the popular cosmology, whatever it is, depends upon a violation of the second law of thermodynamics, which is
No,
not
because
demonstrable?
there is no. It's not like we're putting. It's first, the universe doesn't have a center.
Well,
it's
yeah,
infinite.
sure. Whether center or not.
And it's uniformly filled with radiation.
Mm-hmm.
So it's already equilibrated. So the gas has distributed itself throughout all of the volume of the universe.
Okay, so is that possible to demonstrate, let's say, gas pressure adjacent to a vacuum without a barrier between the two? Is that demonstrable in any way?
I'm not sure.
Let's say I have a
understand the
pressurized.
meaning.
Let's say I have a pressurized shoebox inside of a vacuum. I poke a hole inside that shoebox. Is there any way to demonstrate air not going into the vacuum and staying inside the box, as opposed to?
I don't think so. I think you're absolutely right. If you poke a hole, it will go out. I know. I can't think of unless you just put the shoe inside a very dense, much denser gas or something like that, or put it inside like water or something. I don't know.
So it's true to say you can't have gas pressure in the midst of a vacuum without a solid container.
Yes.
Okay, so how is it the case that we have atmosphere on Earth without a solid container?
Because it's attracted to the Earth
via gravity,
by
right?
the gravity.
But why doesn't gravity hold air in the shoebox?
Because the shoe doesn't have enough gravity.
The Earth presumably does.
Earth has a lot of gravity.
The Earth is inside,
and the shoe doesn't.
So why doesn't Earth's gravity hold the air inside the box?
Because, sorry.
Why doesn't Earth's gravity hold the air inside of the shoebox, which is in the midst of a vacuum?
Because the gas has pressure. So it has pressure and it just
goes out into the vacuum.
Sorry,
I'm just saying.
I have people waiting and I need to go.
Got it. All right.
You think supermassive black?
So there you have it. Now you know what happens when you take basic flat Earth and thermodynamic and cosmological questions to top physicists and astrophysicists and cosmologists at various universities, whether they be that of Carnegie Mellon University in the case of Ira A. Rothstein, or in the case of Simon Fraser University, which is the home of Dr. Pagosian, a specialist in cosmological tests for gravity. When asked questions of the kind, which should be very simple to answer, pertaining to gravity and gas pressure in a vacuum, professors of this high status either resort to snark, evasion, or are simply flabbergasted and have never been asked by anyone any of these questions. So this should give you resolve and comfort to know that there's not much to it. So I encourage you guys, if universities ever open out for you guys, to just go out and visit any open lecture you can and present these exact kinds of questions to your local professor. All right, if you like that, like, share, and subscribe, and so on and so forth. Bye.
Common trend we can identify if we look at the human history and human attempts to understand the universe. The one trend I could think of is that it never turned out the way we wanted it to be. And I don't mean all the ancient people who thought that the Earth was resting on the backs of the whales, or that it was surrounded by celestial spheres. I'm talking just about the last 100 years.
She retarded.